Session 2 on graphs, and we are going to talk about the depth first search. So first of all, what is depth first search? Clearly, as the name says, this method of traversal is going to explore a branch all the way to the end before it starts exploring the neighboring branches. So just suppose that this is how a graph looks like. Suppose this is a hypothetical graph. It looks like this. Okay, just assume that all the edges are downward for now. So I've intentionally drawn the graph like this. So if you start, let's say, a breadth first search here, then the breadth first search says that explore all the neighbor first, then explore all the neighbors of the neighbors, then their neighbors. So you can see it goes from, you can see in the terms of distance. First, all of the things that are 1 unit away, then all of the things that are 2 units away from this source are explored. And in that way, you move forward. That's breadth first search. You explore the breadth first before you go to the depth. As opposed to the depth first search. Which we are going to talk today. Depth first search will say, suppose you want to start the depth first search from this location. Then explore any of this path. Doesn't matter which one, it's up to you. So if we decide to explore this path, then we will not explore the neighbors till we have gone down this path completely. So let's say you go from here, you go from here to here. All the arrows are downwards. Then from here you have 2 choices. So once again, you make the same decision. You go, let's say this path, and then you go this path. It will be like this. Suppose this is the graph like this. Then after coming here, there is no outward going path. So you stop here. So that's the end of one path. What do you do then? You come back to the first neighbor, to the first parent, sorry, to the first node that has not been fully discovered yet. So you say, okay, this path was discovered. What about this path? So you go around this path, but you have discovered this node through this guy, through this link. So it's okay. You don't do anything. You go back and you go back all the way to this place again. And then you explore the second route. Here you come, then you notice there are 2 routes, 2 streams. So you go this way, then you notice that, okay, this is already explored. So there's nothing to be done here. You stop there and you move around this direction. Then here also, this is already explored. So there is nothing to be done. You come here. Then when you come here, you notice that this is explored. And then finally, once this is done, you go to the third path this way. So depth means you go in one direction all the way to you can go. Then you go to the next neighbor and you go to like in that direction all the way that you can go. That's essentially the depth first search. So if let's say this is the graph. Let's take this graph. Okay. And if I do depth first search here, and let's say I begin with A. Then A has 2 neighbors, B and D. You can choose anyone you want. So let's assume that you chose B. So then you go B. From B, you have 2 routes, D or E. Suppose that you went to E. All right. So once you go to E, there's only one outgoing path from E to F. From F, let's say you chose Y, then you chose X. You went this route. Once you're done this, then you come back to the very first node, which was not explored. So you'll explore this. So this might be, let's say C. And then finally you go back to B. The only remaining node is D. So you go to D. So that's the depth first search traversal. There can be other routes as well. You could have very well chosen this as the first route to go, and the answer would have been slightly different. But that doesn't matter. Algorithmically, you will be able to achieve the same result in the end. If you're exploring, if you're exploring, let's say that there is a route between source and a destination, you will be able to achieve it with the depth first search or the breadth first search the same way. So depth first search has there are two ways to implement depth first search. One is recursive, which is very intuitive. And it's useful in many situations. And the other is iterative, which is also pretty good. I mean, for some situations, I mean, iterative code seems to be faster than the recursive code. And if you can do it easily, then I mean, it's always good. You can do the iterative way of depth first search. But let's look at the recursive code first. So what I'm going to do is I'm going to use the same graph, and let me open my IDE. That should also have the source from the previous session. So essentially, for the people who are attending this for the first time, this is the graph, and I have represented this graph in the form of an adjacency list. Okay, so let's say node A has two neighbors B and D. The B and D are in the form of a list. I'm writing Python code right now. This is a dictionary graph, which essentially is representing my graph. And there are two neighbors to A, B and D, this B and D. And that way this whole graph is there. And I've coded BFS already. And we ran the BFS code as well last time. Let's run this again. That was the BFS traversal. Now let's write the DFS code. Okay. So what I'm going to do is I'm going to write code right from here. Once again, you have to provide the graph that you want to run DFS on and the node where you want to begin. Right? You may begin from any node. Any node can be your source, essentially. So I want to start with, let's say, the node A, or sorry, my mistake, a generic node, let's say V, some node V. When I call it, I'll call it like this. I will say DFS of graph and A, to begin with A. Now, how do I do that? Let's talk about the algorithm. I explained to you like how you do it, like in a human way, but how's computer going to do this now? So once again, the approach is kind of same. That, just get rid of this. All right, the approach remains same. And that approach is whenever we are going down a path, writing recursive code is going to be easy. The only important thing is how do we make sure that we don't end up exploring the same path again and again? For example, in this case, you may begin with, let's say, A, D, E, F, C, Y, X. And then when you go with route B like this, A, B, C, and you might end up doing this whole thing again. So you need to remember that somehow this has been explored already. That is the key here. So how can you do that? Basically, you will essentially have to create some kind of a structure where you can remember that this has already been explored. So you have to do that. So how can we do that? We use a set data structure of everything that's already seen. So initially that structure is empty. We begin with, let's say, node A, then we put, let's say this is the structure, we put A in that. And then we say, okay, let's start exploring the other neighbors. So once we are done, D, E, F, C, X, and Y will be in this pool. Once you explore the B branch, B will go here. But then as soon as you go to E, you will notice that the E has already been explored. So nothing needs to be done now. And that's the end of DFS. So I'm just going to code this, right? First, I'm going to write the recursive code. Now, when you're writing recursive code, right, you will need some kind of a structure to be either passed in the recursive function, that's one way, or you can just create a global variable. Let me explain, maybe it will be easy to explain with the code. Suppose I'm going to create a set, and notice that I'm creating this set outside the function at the moment. Okay, for example, in the BFS, I created inside this function. I'm creating outside the function at the moment, and I'll explain what I'm trying to do. So suppose you have this. Okay, so what is DFS going to say? The first thing is, you want to, this is a recursive function, right? The very first thing is that if this node, if V is in scene, then don't do anything, just return from that point. If V is already in scene, right? So that the function will end. That's the base condition for the recursive function. And if that is not the case, then you come to the actual code. That is, what you do is you first, let's say we are printing the nodes, right? So we just print the node. Let's just say V, and then when end equals to something, you print the node. And then you add the node to the scene, because now you have seen this node. So you just write scene dot add this V. So if not seen, if it's already in the scene, then return. If that is not the case, then print this node. That means process this node, then add this node to V. And now recursively call the same DFS routine on every single neighbor. How do I know the neighbor of any of this graph? I'm going to say for neighbor, for example, if I write graph of A, that will return this list. So B and D are neighbors. So I can iterate over this list. And that's what I'm going to do. I'm going to say for neighbor in graph of V. For neighbor in graph of V, basically just DFS of neighbor. Just call the DFS on neighbor. And then if that neighbor is already in scene, then function will return. Otherwise, function will print that neighbor, add that neighbor to the set of V scene, and then for all its neighbor, the DFS will be called, right? So notice that we have a recursion inside a for loop. That means for the very first neighbor we will call DFS. So before the next items in this list, the graph of V are really consumed, we will keep calling DFS till we reach the end of the path. Right? You can just slightly improve this. You can say that only insert this neighbor if this neighbor is not in scene. So I'm just going to add one more condition. If neighbor not in scene, then add this. Otherwise, there's no need to explore that neighbor, right? So let's run this code now, all right? So we run this code. Okay, what is happening? Set is not callable. Where did I do? Oh, my mistake, sorry. What did I do? All right, let's run this code. DFS is missing one position argument V. So I keep doing this mistake. I need to call this in this way, graph, and then the neighbor on that graph. Right, I hope there's no more mistake. Yes, no more. So let's separate this with the print statement. So let me move the BFS call here as well. And then once the BFS call is done, I'm going to put a print statement. So for the same graph, we are going to put now a BFS and a DFS. Right now we printed the result, but it's on the same line. So let's just run this code. And now you get the BFX and the DFS result. They look same because once again, we are doing it because the graph results in the same at the moment. But we can pick a different graph and we can go check that. But essentially, that's the DFS. Just give me a second. Should they be same? They should not be same, I think. DFS of... So let's just run this code real quick here. Okay, yeah, they'll be same. I'm sorry. Yeah, they'll be same because...
No, it should not be, because we have to go.
Because this is the path, right? So what you're doing is you're going to A, B, and then you're going through this D, and then going through E like that. That's why this route is same. That's why they can be same. And similarly for the BFS as well, you're printing A and then its neighbor, which are B and D. That's why it's same. So DFS also goes in this route, and BFS is also going this route. So it's correct.
And also, I think once you get to the node F, if you go if you go back to the graph real quick, once you hit node F, if you hit C and then you hit YX, for DFS you'll go FC, and then you'll hit Y and then X.
Yeah.
And then for BFS you might do the same thing, right?
Yes.
You'll hit C and then Y and then X.
That's right. So that's the that's correct. So that's why this graph is such that what we'll do is later on we'll just switch the graph to something else, and that will help us like having a different result for these traversals. But that's the DFS code. So you notice what we're doing once again is a recursive code. If it's seen, then don't do anything. Otherwise, process this node. Right now I'm just printing, but when we do some real world problems, you'll have to do something here instead of printing. But this template would remain same. Once you have processed that node, you add it to the set of scene. Now, if you don't want to use this scene as a global variable, which I created, then you have to pass the scene in the function as well. And then you can pass it every single time here, like that. So then at that point, basically, you will not have to like have a global variable in that matter. So you can just call from here and then just say some set, like scene once. So let me get rid of this. That's the recursive code. Any question? Let's come to the iterative code. And iterative code is actually used a lot, so it's good to visit it as well. Now, whenever we want to implement recursion, so whenever you want to implement a recursive code iteratively, how do we do that? We essentially have to somehow remember the reverse chronological steps in which we came to a certain point. And we do that with the help of a stack. So in this case, using the stack would be really simple, right? So what we can do is, for example, we can have a stack and initialize it to, let's say, emptiness. Initially, the stack is empty. Then we put the very first node that we want to explore in the stack. Then we run a loop on the stack and we say, okay, bring whatever is in the stack out, like the first element. So A comes out of the stack. Okay, let's just remove this. A comes out of the stack. Then we say, okay, who are the neighbors of A? Let's put them in the stack. So we put B and D in the stack. Okay, those are the only neighbors. Okay, now once again, stack pop. So we pop the D out. So the next element is D. Then we say who are the neighbors of D? There's only one neighbor. Push that in the stack. So essentially, we push E in the stack. Now notice what stack is doing. What stack has done as compared to the Q in the BFS is that stack is keeping B at the bottom of the stack. So we'll not reach it till we have explored this path that we are exploring right now. So once again, we will say, okay, who are the neighbors of E? First we bring E out. Who are the neighbors of E? F. So let's bring the F in. And this will go on. So then we will say, okay, who are the neighbors? Then bring the F out. And then who are the neighbors of F? The neighbors of F are C and Y. So we put C and then you put Y on the stack. Okay, then take Y out. And who are the neighbors of Y? X. So let's put the X into the stack. Okay, then remove the top of the stack, X. Then who are the neighbors of X? Nobody. Okay, loop ends. Then who are the neighbors of C? Nobody. Print C, and then nobody is its neighbor. Then we go to the next, pop the stack again, B. Who are the neighbors of B? D and E, but they are already seen. So nothing needs to be done. So that way you can do the iterative DFS. Let's code it up. It's also not very complex. Just give me a second. All right. So I'm going to write the DFS iterative code. Okay, DFS, and let's just call it iterative. And the DFS iterative is also going to look for a graph and a node to begin with. So let's call it, let's say V. Okay. So the very first step in the case of a DFS iterative code is going to be that first we initialize a stack, as we said. And in this case, this is just a name, stack. I'm just using a list. All right. So this list is an array in which you can add item at the end by using pop, by using append, and remove the items using pop. Okay, so this is just a list. And let's initialize that list with the very first element, which is V. And then we create the same set, scene, which is a set. And then we write it the same way that we write a BFS. Look how the BFS code was similar. I'm going to say while this stack. That means that until this stack is empty, I'm going to do something. Okay, I'm going to say, first of all, pop the current node. So stack.pop. So when there is a list and I do list.pop, that means the last item is removed from the list. Okay, let me just open the terminal real quick. For people who are not familiar with Python, just not only it pops, it removes the items as well. So suppose you have a list, which is something like, let's say 1, 2, 3, that's the list. And if I do l.pop, then that removes 3. That's the last item comes out, and the list is only 2 items remaining. So I'm just going to do stack.pop and bring that item into current. Okay. Now I have to check if this item has already been processed. So I can check if whatever. If current in scene, then basically don't do anything, just continue. Just end the loop. I mean, just go to the front of the loop again. Else, if we have not already seen it, then what you have to do is, actually, let's do it the opposite way. If current not in scene, because we don't need to handle this condition. If current not in scene, then essentially print current. Let's end it with remark like this. And then just add scene.add current. And once you have done this, you will just say for neighbor in graph of current, add them to stack dot append current. Sorry, neighbor, all the neighbors. Let's just append them. So what my algorithm is doing is basically check here. Current is equals to stack.pop. If current is not in scene, then essentially print the current and add the current to the scene list. And then for all the neighbors of current, just append it to the stack. That's all. So that should be good as far as I can think. But I mean, you can add a little bit of optimization here, and you can just say if neighbor not in scene, then do that. This much you can add. So let's run this. Let's run a print. Okay, and what I'm going to do is no, actually that's a local function. Yeah, that's fine. And let's go here, DFS underscore iterative, and put graph and then A. Right, it should be fine. Let's run this code and see what we get. Now you notice in this, that's the DFS for iterative. And now you see that the output is slightly different. And why is the output different from this one? Can anybody tell me? Why is the DFS recursive and DFS iterative outputs are different?
Does it have to do the way with their, I'm guessing it has something to do with that list. The way the list is, so you're implementing a stack using a list, but previously you were still doing a stack, but using like a function call stack, right?
Yeah.
Whenever in recursion, you're relying on the function call stack. So something different with the way Python, I guess, it treats a list.
So I think, I mean, you're right there, but let me just quickly explain why this output is slightly different. And the reason is this. Let's copy these two code snippets here. Okay, let's just copy this recursive code snippet and let's see how this recursive code is being called here. This part. Okay, let's just put it here. That's the recursive part. And remember how the graph is. Okay, let's just copy a little bit of graph as well here. Let's copy the graph here as well. And notice how this recursion is going to work. The recursion is going to say, for neighbors in graph of V, let's say the node was A to begin with. So for neighbors in graph of A, which are B and D. So first we'll process B and then D. If neighbor not in scene, don't worry about this line. Graph of neighbor. So the two neighbors are B and D. So we first process DFS of B, and then we process the DFS of D, right? So the first result has this A, B first, and then D is the neighbor of B, so you get after this. The other implementation, if you notice, we have a stack, and how it actually works is, copy this. We say for all the neighbors of this graph, right? Look, you say for all the neighbors of this node, call DFS on each one. But we are saying for all the neighbors of this node, put them in the stack and append them in the stack. So let's say if A was the node, then the stack will have B appended first, then D appended after that. So once you go to the top of the loop and you do the pop, the D is going to pop out first, right? Because once again, we access the list from left to right. So recursion starts the search on B first, whereas if you put in stack, then the stack is going to pop D first. That's why it's the opposite of the recursive. But nevertheless, it's DFS. Does that make sense? Okay, let me know if you have any question on this. So that's DFS in two ways. We have implemented DFS recursively, and we have implemented DFS iteratively. Okay, and I'm just going to hold the time complexity for a bit more, all right? And we'll talk about it. Yes, question.
Yeah, so what if we do pop 0 instead of just pop?
That's a good question. If you do pop 0, that means we will get to the same output. But I think what you mean is not pop 0, but you mean the reverse of the list. So you want to say, let's say, reversed of this. If you do reversed of this, let's try to see what happens now. Once you do that, now notice the output is same. Right? Because whatever the neighbors are, you reverse them. So then once again, D will be inserted and then B will be inserted. So when popped, B as in Bombay will come out first. I think that was your question, right?
Yeah, it explains in Java. Yeah, thank you.
There are two important things that I want to discuss. So one is cycle detection. And another is topological sorting. Okay, both are very important. And I want to talk about these two. So I'm hoping that I'll be able to finish all of this by the next session. And maybe a problem on this. So first of all, what is a cycle detection? Let's talk about it. You have a directed graph, assume like this. A, B, C, D, and E. And it's like this. A cycle means that at least on one path, if you start, then you will end up on a node that's already on the path. So in this case, for example, this graph does not have any cycle. If you go from A, it will go like this, and that's the only route we have. There cannot be any cycle here. Similarly, from here, if you go, you will reach here. There is no cycle. But if you change these arrows a bit in this directed graph, if you change the arrows a bit, suppose that what you do is let me add one more node here with this. Suppose you have this node here like this. Then you have a cycle. So if you go here, A, if you start from A, then you go to C, D, and then when you do DFS, after that, you will reach E again. And then if you continue your DFS, then you are essentially in an infinite loop. You will just continue doing this. So the one important thing that the scene set, the set of scene that removes the hurdle that it removes us, that it keeps track of everything that we have seen so far, and we don't end up getting into a cycle. But the problem is that it cannot really detect a cycle. So cycle detection becomes an important part of process. Let me give you a real life scenario. Okay, so this is a question that has been asked as well. Suppose that when we write code, right, in the initial part of the code, we describe the libraries that we are dependent on, right? So we say, let's say we are using import. Let's say there is a file A, and you may say import B, and then let's say import C. Then file B may say import C, and C may say import D. Right? Then in order to optimize this, the compiler, essentially what it creates is it creates a dependency graph. It says that the A is dependent on B and A is dependent on C. So in order for A to really execute, we need to execute B and C first. But B is dependent on C as well. So in order to execute B, we need to execute C first. And C is dependent on D. So in order to really run C, we need to execute D first. So in order to run A, we first need to run D. Then we need to run C, then B, and then A. Okay. There's something called topological sorting that we're going to talk about maybe in the next session. But you can see how the dependencies are compiled when you run your code. However, there is a problem in this situation. Consider that, let me say this. Okay. Consider a situation where you have a module A dependent on B and A dependent on C. Now let's say B is dependent on D and D is dependent on, say, D is dependent on C and C is dependent on B. Right? So there, what happens here is that there is a cyclic dependency. So in order to compile A, you need to compile B and C. In order to compile C, you need to compile B. Right? So then there is no real order in which you can compile things because B is dependent on D, which in turn is dependent on C, C is dependent on B. So this is called cyclic dependency. How will you compile this? There is no element that you can pick that you can compile really first because everything is dependent on everything else. And suppose that you're a compiler, right? Suppose you're a compiler and you want to flag this. As soon as you find this out, you want to flag this, that there is a problem here, that there's a cyclic dependency. Then how do you do that? Once again, let's write the dependency graph for this. So A, the neighbors are B and C. For C, the neighbors are B. For B, the neighbor is D. And for D, the neighbor is C. That's the cyclic dependency. Now, suppose you want to detect a cycle in a graph. Okay, suppose you're given this graph and you have to find the cycle in the graph. This kind of question can be asked actually in different formats, but essentially it boils down to this, that if this thing has a cycle, then it's a problem or it's the solution, whatever. So how do you go about this? If you just do depth first search, that probably will not work. Depth first search will just return the answer. You will have to do something more than depth first search. Okay, I'm just going to redraw this here. A to B to C, then to D, If you just do depth first search, then you'll visit A, B, D, C, and then B is already seen, so you will not process it. What you need is a list of libraries, list of nodes that are already under processing. Okay, so consider that when we start the DFS, the usual DFS, and then we have an additional data structure. That data structure keeps track of everything that we are currently processing. Right? That data structure is able to say that if we process a path like A, B, D, C, and then we go to a node B, which is already present in our current path, then there is a cycle, right? This is the presence of cycle. If we do DFS and we can keep track of the current path, and we know that there's a back edge coming from a node to the current path, any node in the current path, then there is a cycle. So that can be done using an additional data structure. First of all, any questions so far? All right, so let's see this. First of all, algorithmically, how we're going to do this algorithmically. Instead of, we keep a set of, let's say, scene, everything that we have seen so far. Instead of scene, we have another set. That set, let's say, is called path. Or maybe it's a list. Let's just keep it as a list for now. It doesn't matter. There is a list, which is path. And it is a list of the path that is being currently explored. And I will populate as we go more forward. Suppose that we are processing the DFS. So we start with the node A. Then we say, okay, A is in the path. Okay, process A, print A here, and A is in the path now. Okay, and A is also seen. That's okay. Then A has two neighbors, B and D, and let's say we process the path from B first. So we go from B and we print B. You're doing DFS essentially. So the path B gets added in the path right now. Then you go to the D gets added in the path. Then you go to C, the C gets added in the path. And then you go to from C to B. As soon as you add B, and you notice that the B is already present in the current path, okay, the path that we are on, that means that there is a loop here. And we need to flag. This path is different from scene. Okay, I'm taking a simple example, which is why they both look same, but essentially this path is different from scene. This path is the current route that we are on. And if, let's actually take a better graph. Let's take a bigger graph than this. So let's suppose you start with A and then you go to B and C, D. Let's say that, this here, and let's put this here like this. Okay. So let's do the same thing again. Okay, there's a set of scene, and then there is a path. And you begin with A. I hope this should be a good example, but let's see. Okay. So from A, we explore A first, so we put A in the set, and then we say A is also in the path now. And we go to B. When we go to B, we put B in the scene, and we put B in the path. And we go to E. Actually, let's just take it real quick, real back. Let's process C first. So C is here and C is in the path. Then we go to D. D is here, D is in the path. Okay, once we have reached the end of this, so we go back to the C and we go to the next neighbor of C from here. Once we back up here, the scene remains same, but once we back up here, the D is no more in the path, so we remove D from this path. Now this is path is this. Then we go to E. So E is in the scene and E is in the path now. Then we go to F. F is in the scene, F is in the path. Then we go to C. As soon as we go to C here, if we were DFS, we would say that if we were just doing DFS, we would say that okay, the C is in the scene, so let's not do anything. Let's stop it here and continue forward on the next path. But now with the help of path, we know that in the current line of path, the C already exists. This essentially means that there is a loop that starts with A, goes to C, then E, then F, and then there is a back. There is a cycle present here. And this cycle essentially can be checked with this additional path structure. Now, this can be a set as well. If you notice, this can be a set. This set can be the set of things that are currently being explored. Different books provide different types of algorithms. So some people say that as soon as you see this graph, you create three sets: white, gray, and black. White is all the nodes that we have not seen so far. So everything in this graph is in white. Black is everything that we have processed and there's nothing need to be done. And gray is everything that is currently under the current processing stage. So in the gray, you keep the current path. But sometimes you may be asked to provide the path, the cycle itself. And you may have to print that cycle like this: A, C, E, F, and C, that this is the cycle that we're talking about. So, or this C, E, F, C, this thing. And so keeping a path might be helpful because in set, there is no way to retrieve that serial link. So that's an example of cycle detection. And I'm going to code this. Let's end the session today here. Okay, I'm going to end the session a little bit early today. Let's end it right now. And then I'm going to code the cycle detection and the topological sorting in the next session, which is the last session for this particular year, for this year. Any questions?